Welcome, everyone. The title of today's webinar is Building Better Models for Hysteretic Dynamical Systems Under Uncertainty by Dr. Patrick Brewick. Dr. Patrick Brewick is an assistant professor at the University of Notre Dame. Prior to joining the University of Notre Dame, he was a research scientist at the US Naval Research Laboratory. Dr. Brewick received his bachelor's degree in civil engineering from the University of Notre Dame, his MS and PhD degrees in civil engineering and engineering mechanics from Columbia University. He pursued his postdoctoral research at the University of Southern California prior to joining NRL. Dr. Brewick's research focuses on exploring the connections between data analytics, modeling, and mechanics. Please welcome Dr. Brewick. The floor is yours.
Professor Ghosh, thank you so much for that kind introduction. Thank you to everyone who's joining us today. So, gotta get started here. There we go. So I think that we would all agree that as engineers, we rely upon models every day in some capacity, right? Perhaps we're doing more theoretical, foundational type work where we're using analytical models, ODEs, PDEs. Perhaps, again, we're very computationally focused using things like finite element models or maybe something more like CAD or BIM. Or perhaps we're doing something more conceptual where we're using surrogate models, where we're representing some mechanical or physical relationship through some sort of abstraction where we're treating things as inputs and outputs. But I would argue that it's very likely that all of us gathered here today probably interface or interact or utilize models in some capacity every day. But unfortunately, sadly, all of these models are in fact wrong. And that is less so my belief or opinion as much as it is a very astute observation from the great statistician George Box, who commented that all models are wrong, but some models are useful. And so I think the real key is how do we create useful models? And so what we desire are models that are informed. So if we imagine that we have, say, our real system, our real mechanical or physical structure that we're concerned with, what we want are models that are informed. And what that means is that we want to be able to take advantage of whatever sensing data, telemetry, measurements, observations, whatever data we can get. If we can take that data from our real structure and use it to inform our model, again, whatever type of model we're using in that virtual space, then we're making our model more informed. And if it becomes more informed, it is likely to become more accurate. And if it's accurate, well, then there opens the possibility that our model can become predictive in the sense that we could take model outputs and use that information to tell us something about the real world system. And if we manage to accomplish this, we have a nice sort of feedback loop here where sensing information gives us data that can inform our model. Our model being informed is then giving us predictive outputs that give us information that tell us something about the real world system that can inform decision making, inform design, right? This is sort of the goal. And the phrase that's used a lot right now is digital twin. I apologize if I am the about 1 millionth person to use that word, but I know it's a very buzzy term, but I think it represents something important because the idea of a twin shows that we want our model, our virtual representation, to truly be a useful, faithful representation of whatever real mechanical or physical system we're concerned with, right? That is the ultimate goal. And if we do that, if we manage to accomplish that, useful models have all sorts of applications. We can utilize them for monitoring structural health and damage. We could utilize them for simulation, additional load cases, possible threats or hazards, for optimization purposes, for both design elements and design modifications. I bring up design modifications because, as Professor Ghosh mentioned, I spent time at the Naval Research Lab prior to joining Notre Dame. And their modifications are a really big aspect because many of their assets and platforms are already in service, and questions arise about their performance where a design modification has to happen. You don't get the privilege of designing from scratch. You rather have to make a design from the current state, hoping to then project how it's going to perform in the future. And so if we have a useful model, that can be really helpful in understanding how we can make those modifications. And then there are also tasks like forecasting, service life, degradation, reliability, resiliency. There are many things we can utilize a useful model for if, in fact, again, we have made it useful. However, despite all this progress, our models still aren't perfect. So here before you see a picture. This is one of the ships from the LCS class. For those of you unfamiliar, the LCS class stands for Littoral Combat Ship. I bring this up as an example because in May 2022, this entire class of ships was retired from service without ever having a single ship complete a single mission successfully. Now, there were myriad reasons for that, ranging the whole gamut of everything from economic and political reasons. But in the congressional report for the retirement of this entire class of ships, one of the specific items cited was repeated failures or structural failures due to high stress concentrations. This particular class of ship failed because there are still challenges at the interface of data modeling and mechanics that we have not appropriately solved. So even in this case where we have a multi-billion-dollar program where we're spending all sorts of money putting sensors and telemetry and data gathering devices on these ships, we spend millions of dollars developing their models. We infuse it with all sorts of mechanics theory to try and understand stress concentrations and understand cracking and fatigue. We still failed to do so, right? Structural failures were one of the reasons this entire class was retired and retired early. And that's clearly a failure of modeling, but specifically at this interface of data modeling and mechanics. And this interface is challenging because it involves tasks of data assimilation, model selection, calibration, validation, parameter estimation. But sitting on top of that is the reason we're all here today is uncertainty, right? Uncertainty is sort of the wrapper around all of these challenges that only amplifies the task at hand or amplifies the challenge of we have to solve this complicated interface problem of the data we're gathering, the model we're developing, the mechanics we want to infuse it with, and we have to accomplish these tasks, but knowing that uncertainty sits on top of all of that. And so with that in mind, I want to talk about a few projects that I've been engaged in over the past, I say both weeks, months, years. And so the first one deals with model selection, but as with all these project titles, they're always going to deal with model selection under uncertainty, calibration, surrogate modeling under uncertainty. So for model selection, I want to talk a little bit about a project I had with eDefense. For those of you unfamiliar, eDefense is part of Japan's National Institute for Earth Science and Disaster Resilience. They have an incredible shake table facility, and it's a fully 6-degree of freedom shake table that can do full-scale testing. So in this case, they tested a 4-story building. And again, the building weighed nearly 700 tons. It had full dimensions. And it was sitting atop a passive isolation layer that was then resting atop their incredibly impressive shake table. And the objective of all this series of tests were to look at how the energy dissipation devices in this isolation layer would respond to different types of excitations. And so there were several different devices used in the passive isolation layer, which is what makes this so fascinating, is it was a hybrid layer. So the layer featured rubber bearings, which you can see here in green, in these 2 corners here, as well as elastic sliding bearings in these other 2 opposite corners. And these are flat surface frictional sliding bearings. And then there were steel yielding dampers, and these are U-shaped steel yielding dampers. And they're in pairs where there's one oriented in the X direction and one oriented in the Y. So there's one pair at each of these 2 locations. So again, it involved a variety of devices. And additionally, there were other tests that incorporated a set of controllable oil dampers, but that's not really subject of the discussion or study today. So I was part of this larger project to sort of develop a surrogate model for the entire structure. How are we going to create a computational model that can represent this test structure? And that involved challenges of system identification, finite element modeling, controllable damper design. And today I really don't want to focus on the model selection calibration aspect. Right? I was part of a team working on many aspects of this project, but I want to focus today on specifically the model selection and calibration, because if our goal is to develop a surrogate model for the entire building structure, we're going to need a nice model to describe the seismic behavior of these different devices. And so we have to then identify a proper model for these devices. And there are many models that we can consider because there's many ways you can model a hysteretic response. We could use polynomial models such as the Clough or Takeda model, very classical approaches. There are differential-based models like that suggested by Bu Guen and very recently by Viana and Rosati. And then there's also equivalent linear models where AASHTO, JPWRI, Caltrans, they all have their own equivalent linear models as well. And all of these have been used in different studies to represent the nonlinear hysteretic behavior of isolators. And so we're going to focus specifically on those steel damper pairs. I want to focus on those because they happen to have exhibited very strong nonlinear behavior over the course of testing. And they also did show some evidence of wear over the course of testing too. And in terms of the testing itself, I present to you this matrix. I realize it's a bit of a eyesore. It has a lot of information in it, but the point of this is just to show you how many tests were conducted over the 2-week period. In total of 50 tests were conducted. over this 2-week period. So these isolators were subjected to a lot of different excitations at different intensity levels. And so this then led us to ask, well, what is going to be the best model to describe their behavior? Because, for instance, for one set of tests with one particular set of excitations and intensities, we see a response that looks something like this. And then we change the ground motion, we change the intensity, and we get a slightly different looking response. And it got us thinking, okay, well, what model will best describe this observed behavior? So we considered several different models for these steel damper pairs. We considered a bilinear model, and this was based largely on the fact that the manufacturer provided a pre and post yield stiffness as well as a yield displacement in their specifications for the dampers themselves. So bilinear seemed like it would be likely very appropriate. However, we also wanted to consider the Buchwen model, right? This is one of the classical differential-based models used to describe nonlinear hysteresis, has been used extensively for seismic isolation devices. But over time, there have been variants developed, including the degrading Buchwen model, which was introduced by Baber and Wen. And this one includes degradation functions, so you can sort of have an evolution of some of your model parameters over the course of a simulation or a test. And also, Song and Jakurigan suggested the generalized Buchwen model, which includes features to help highlight asymmetry, so if you have an asymmetrical response. And again, given some of the restoring force displacement loops we saw, we thought, oh, maybe this asymmetrical model might be a good choice. And then Vaiana and Rosati, very recently, just in the past 2 or 3 years, have started suggesting their own differential-based model that includes an incredible amount of flexibility to describe a wide range of hysteretic behaviors. And so these all seemed like possible models that could describe the behavior we were observing. And importantly, where possible, we wanted to implement this in a biaxial fashion because we know that with these two dampers oriented in the X and Y direction, as well as the 6 degree of freedom excitation being serving as input, we're likely going to get some biaxial effects. We want to make sure we have a biaxial model as well. So the objective then is to choose the best model. And for this, we're going to look into Bayesian model selection, right? Finding the most probable model considering the available data. We can express this, right, as essentially what is the probability of a given model or model class based on our data. And then using Bayes' theorem, we can expand this out. And if we consider the fact that our dynamical data sets include both inputs and outputs, we can then do one further extension of this. But truthfully, the real challenge when it comes to implementing Bayesian model class selection is evaluating this quantity, which is called the evidence for a given model or model class. And the issue is that when you're evaluating the evidence, you have to evaluate the model given whatever parameter vector theta describes that model. And that means you then have to integrate over the full domain or the full parameter space for theta. And if theta, again, has an increasing dimension, you're going to have an increasing dimensional integral. And so clearly this can become a computationally intractable problem, right? We run into some real dimensionality issues depending on the size and extent of theta with this. However, luckily, some people much more brilliant than me have suggested methods of how we can overcome this challenge, including Skilling, who's put forward this idea called nested sampling. And the brilliance of nested sampling is really in its simplicity, in that it converts the evaluation of this evidence integral from something that's sort of computationally intractable and challenging to something that's actually an incredibly tractable summation. And this is accomplished through a pretty simple change of the order of integration, which eventually reduces everything to just a simple quadrature rule, where, as you can see here, you're essentially just climbing up the likelihood function. Now, I should point out that this here is a sort of a nice cartoon graphic for a fairly straightforward likelihood function, but there are variants and extensions to nested sampling to handle bimodal, multimodal, and other more complex likelihood functions as well. So it's very well suited to evaluate evidence even for more challenging modeling cases. So once we know that, we actually now have to define the likelihood. That then becomes the main task. And we're going to define our likelihood function in terms of the error between our predicted restoring forces and our measured or observed restoring forces. And we're going to treat these errors as being independently and identically distributed zero mean Gaussian random variables. As such, our likelihood function becomes a nice expression of the product rule, where again, our error is just given as that deviation between our model prediction and measurement. But again, given that the topic of these seminars is about uncertainty, let's make sure we talk about the fact that our error variance is going to be a very important quantity when it comes to evaluating this likelihood. And so in particular, we had to conduct some preliminary analyses in terms of how we were actually going to quantify this error variance. And one of the decisions we decided to make was to treat the X and Y directional restoring forces as having the same variance to ensure that there was no bias in terms of the likelihood function for one direction over the other. And after our preliminary analysis, we arrived with a value of about 7 kilonewtons for our error variance. And I realize that seems like an incredibly specific detail, but I will return to that later in this talk. Now, once we had the error variance settled, we also needed to deal with the fact that some downsampling was necessary because the original data provided during experiments was sampled at 1,000 hertz or 1 kilohertz. And for those of you who do some structural dynamics, you'll know that that's an incredibly rapid sampling rate. And from a probabilistic standpoint, this also creates some issues because if our likelihood function is dependent on the product rule, and we're sampling data at 1 kilohertz and we have responses that are 100, 200, 300 plus seconds long, we end up with so many data points that our likelihood function becomes incredibly narrow and essentially moves all of the uncertainty away from the parameters and just into the prediction error itself. So to sort of deal with that challenge, we looked at some downsampling factors of 10, 20, and 40, which then give us new sampling rates of 100 hertz, 50 hertz, and 25 hertz, which are much more in line with what we typically have for a structural dynamics experiment, and still have sufficient frequency resolution in terms of the Nyquist frequency to capture the frequency content that we need. Now, we're going to calibrate, and this is the time we have today. I want to talk about calibrating models using two different tests. Again, here we have our test matrix. And so one of the tests we're going to use is from the KNet Furukawa record from the Tohoku Oki earthquake from 2011 in Japan. So we have this record here. And then we're also going to look at a record, specifically the J.R. Takatori record from the Kobe earthquake from 1994. And as you can see from these two plots, they're very different types of ground motions, very different types of excitations, although in this case, they were scaled to have, I'll say, close to comparable intensity, right? But just very different ground motions in general. So we go through the process with our 5 different models. We evaluate the evidence. We then compute our posterior model probabilities. And we see that using this Tohoku Oki earthquake record from test 14, our posterior model probability is essentially 1 for our degrading Buchwin model. And this was surprising for a few reasons. One, we thought there'd be a little bit more parity. We thought we wouldn't necessarily have one model be so dominant in a posterior model probability sense. But also, we were just surprised that a model with more parameters was identified as being most likely. However, we can look more closely at the maximum likelihood estimates, or MLEs, for these different models, classes that we're considering. And we can see that the bilinear model, the Bayano-Rosati model, don't necessarily present the best match. The Bayano-Rosati performs admirably, but maybe not the closest in terms of the observed behavior. But then if we look at our Buchwin models, we can see that we have the generalized, the conventional or standard Buchwin, the degrading Buchwin. And looking at all 3 of these qualitatively, it's actually pretty difficult to judge which model is better capturing the restoring force. And so working with my student on this, we sort of had the thought, well, if it's qualitatively difficult, why would it be that one model necessarily has a posterior probability of 1? And specifically, why would the degrading model with a larger degree of parameterization outperform the standard Buchwin? Because typically Bayesian model selection applies, the model of parsimony, that all things being equal, like a simpler model is the best explanation. So we wanted to dig into this a little further. And so we first considered some alternate criteria. So beyond just Bayesian model selection, there are other model selection criteria, such as Akaike's information criteria, Bayesian information criteria. And these are particularly interesting because they include explicit penalty functions for the number of parameters, the number of measurements that you're including. And so our thought was, well, is there any way in which these penalties are actually going to help us understand or explain what we're observing? But when we apply this to our model classes, we see that whether we're using the AIC or the BIC, the degrading Buchwin is still selected as most probable and with similar margins as compared to the Bayesian model selection. So that got us thinking a little bit more about the degrading Buchwin model itself and thinking about the model form. So here you can see the equation for the degrading Buchwin model. And I have below these 3 sort of degradation functions that are included. And you'll see each of these depend on a variable epsilon. And epsilon is based on the dissipated hysteretic energy. So we're able to sort of track this dissipated hysteretic energy measure over the course of a test or a simulation or a run, whatever you want to call it. But by tracking this, we can then look at how these parameters evolve. And so we can then look at the evolution of A and nu and eta. And when we plot these using the maximum likelihood estimate values for delta A, delta nu, delta eta, we actually found that only delta nu was really deviating from a value of unity. And what that really told us is that the delta A, delta eta, those values were functionally 0, and really only delta nu was showing some signs of evolution. However, we can use these evolutionary variables to sort of recontextualize the shape functions or shape variables within inside our Book-Wen expression. That'd be beta and gamma, right? Those are the two parameters that control the shape of our hysteresis loops. And we can then use, right, this expression you see here, where we're looking at how beta becomes its own function of time if we modify it by nu and eta, and we can do the same thing for gamma. Then if we plot that, we now have a sense of how beta, or an equivalent to beta, is sort of evolving over the course of a test, and same with gamma. And then we can contrast that with the standard or general Book-Wen, which obviously can only use a constant value. And what's interesting is you realize that the degrading Book-Wen, in contrast to the conventional, has this evolution where the conventional Book-Wen is essentially adopting the time average value of the evolutionary beta or gamma, right? So this right here, this value from the conventional and this one from the conventional for gamma are very close to the time average value for beta as a function of t and gamma as a function of t. So what happens then is the degrading Book-Wen, by being able to track this dissipated hysteretic energy and sort of modulate and evolve beta and gamma over the course of simulation, actually gives it enough performance advantage to justify these extra parameters and therefore make it a better, more probable model given the data we're observing. And so we then had the question of, well, is the same model going to be probable if we then look at excitation from the Kobe earthquake, right? From that 1994 J.R. Takatori record from Kobe. And what we find is, again, we look at our models, we evaluate our evidence, and now, interestingly, the generalized Book-Wen is coming up as being most probable, right? Having a posterior probability, again, of essentially 1. You can see some of the other posterior model probabilities are considered non-zero, but functionally they're still 0 compared to what the generalized Book-Wen is. And so again, this was sort of a surprise, because if we go back to look at our restoring four plots from this test, again, we have that issue where qualitatively they don't look all that different. And so actually right now, I have my student Reza, whose work constitutes a lot of the slides you're seeing. He is currently trying to look into how can we better quantify the impact or effect of those asymmetry parameters inside the generalized Book-Wen to help us explain or understand why it might be a better model choice or a better model selection for this given test. And so he's currently looking at those parameter sensitivities as they relate to these tests right now. So I don't have a great insight yet, other than to say that we're continuing to look into this, but we certainly found this to be an interesting observation. But what we also looked at is we knew that we could compare our model preference against the characteristics of the ground motion themselves. And so we actually did some additional evaluations using tests not just from Tohoku and Kobe, but also some of these scenario earthquakes E-Defense conducted using scenarios for the Osaka region. And we did this for both steel damper pair 1 and steel damper pair 2. And so what I'm showing you here are some different characteristics of the ground motion, say an intensity as an RMS acceleration, a peak acceleration, and I'm plotting that against model preference. And what you can see is that generally the more intense, higher peak acceleration ground motions tend to favor the degrading Book-Wen, and the lower intensity tend to favor the generalized, but there's clearly no sort of easy line of demarcation or clear indication of where that break would be made. And then further, we also wanted to look at model preference against the dissipated hysteretic energy, thinking like, oh, maybe that plays an important role in the prominence of the degrading Book-Wen model. And so you see over here the plots of the evolution of hysteretic energy over several different tests. And then here we're plotting that total hysteretic energy versus model preference. But clearly there's no obvious correlation here, because we have some tests with high dissipated hysteretic energy preferring degrading, but others preferring generalized. And then we even have some cases with a low total of dissipated hysteretic energy still preferring the degrading Book-Wen. And so with that, we can sort of see from this study that my student and I have been working on very recently that the most probable or sort of best choice model for the hysteretic response was not necessarily consistent across tests. And both the degrading and generalized Book-Wen models were able to overcome penalties associated with additional parameters or additional complexity. And for the degrading, we can see that that ability to capture the time changing or evolving parameter relationships gives an advantage over the conventional Book-Wen, which can only sort of use these mean values. And we're actually currently working on evaluating parameter sensitivities to get more insight into this as it relates to both the degrading and the generalized Book-Wen. But interestingly, there was no clear-cut model preference with respect to ground motion characteristics, where higher intensity ground motions did tend to prefer the degrading Book-Wen, lower intensity did tend to prefer the generalized, However, there wasn't a clear-cut indication there. And then also that the magnitude of dissipated hysteretic energy ended up not being a good indicator for model preference. That was a little bit surprising. We were wondering if that might be a good hint in understanding this model preference. But what this all then leads to is this idea of the importance of maybe taking on a hierarchical type of model calibration. So what if we wanted to consider multiple data sets during calibration, right? We want a single model that broadly represents the performance of these isolators across all tests. And so in order to do this, we want to calibrate model parameters in that vector's theta using multiple data sets, and hierarchical Bayesian methods actually offer a pathway for us to do this, both across tests and potentially across devices. And so if we adopt a hierarchical approach, what we're trying to do is find a posterior distribution of our model parameters, considering the test data from multiple tests. And I want to make sure to clarify here that we are here now trying to find a posterior distribution for these parameters. We are no longer engaging in a model selection activity where instead, again, just looking for our posterior distribution. But once we do that, what we end up trying to do with a hierarchical is to define these hierarchical parameters, mu and sigma, that denote the mean and covariance. We want to define the mean and covariance of theta, because that way we can sample from those to then draw samples of theta to evaluate our model. We can then get estimates of our restoring force and then evaluate the error of our restoring force with respect to our measurements. And then we can also consider the prediction error, in this case, the prediction error variance, as its own variable sigma, or sigma I, if you will. And so here you can see an expression of what our joint posterior would look like. And so if we're going to evaluate this, we have to make assumptions. Just as we did in our model selection, we're going to have to assume our likelihood function. And in this case, we're going to, again, treat the errors as independent and identically distributed zero mean Gaussians. We're also going to assume that our model parameters in theta are independent from our prediction error variance in sigma. And in terms of sigma, we're initially going to assume a non-informative prior. We're going to assume we don't really have good information of how we should treat or assume sigma. So we're going to use Jeffrey's prior or non-informative prior for sigma. And if we do all that, we can rewrite our joint distribution as you see here. And then if we follow some of the methods that Sadeghi and his co-authors have put forward in one of their nice papers on hierarchical methods, we can actually marginalize over that prediction error variance. And that yields an expression you see here where we have this new L1 function. And this L1 function is related to our likelihood, although it's slightly different. But the importance is that if we have a large number of data points, which is likely to happen in these tests, even if we're sampling at 50 or 100 hertz, much less 1 kilohertz, if we have a large number of data points, we can use the approximation that the negative exponential of this L1 function is approximately Gaussian with mean theta star and covariance sigma star. Because if we have that approximate Gaussian, we can find then sigma star simply through a minimization of L1 using any optimization scheme that we'd like. And we can evaluate then sigma star as the inverse of the Hessian matrix of L1 evaluated at theta star. And we can find this potentially analytically or through numerical differentiation, right? We can evaluate both of these. And if we have that, we can then further marginalize over our theta I values. And now we have an expression for the marginal posterior distribution of our hyperparameters. And this is what we're really after, because if we have this expression, then we can start to look at finding the posterior that we're really interested in, that of our model parameters in theta, because if we have an expression for the marginal posterior of our hyperparameters, we can simply sample from that to evaluate our posterior for theta. Right? This is our ultimate goal. So we want to implement this for our steel damper pairs, and we're only going to implement it in this case for the Bouk-Wen models, because based on our model selection results, those were clearly the most likely or most probable models. And so for instance, if we did a Bouk-Wen model standard, we'd have 6 parameters we'd be considering. For the degrading, we'd have 9, because we have these additional 3 degradation-related parameters. And importantly, our unknown variables that relate to stiffness, that would be here alpha, our post-yield stiffness ratio, and then our 3 stiffness parameters. We're going to have to use a log normal transformation because we want to ensure that we're never going to get a negative value for these parameters. And so if we do all that, we can just consider the case specifically of the degrading Bouk-Wen, given that's one of the sort of recurring themes of this talk, one of the models we're investigating pretty thoroughly. And we want to perform a hierarchical Bayesian model calibration using response data from multiple tests. And so again, I realize this is a rather ugly test matrix I keep putting in front of you, but we're going to focus on tests that exhibit strong nonlinear behavior. So we select a variety of tests from this. I believe it's about 17 in total. And these tests include the Tohoku, the Kobe, some of the Osaka scenario earthquakes, right? We're taking a nice smattering of different ground motions into this calibration. And once we do that, we're going to evaluate our eventual posterior using a TMCMC approach where we're going to try and generate about 10,000 samples. And importantly, as an implementation detail, instead of directly estimating those stiffness values, we actually want to use a modifier of some initial stiffness guess because our manufacturer, as I mentioned earlier, did provide the pre and post yield stiffness. So if we use that, we can then say, instead of trying to estimate K directly, we're going to see if we have to modulate or moderate that K value. And that way our stiffness parameters are all maybe in the range of 0 to 1 or 0 to 2, much like our post yield stiffness ratio. And similarly, we're going to use uniform priors where our mu of theta is going to be defined over that appropriate range. And obviously the ranges are going to change depending on if we're talking about our shape parameters, beta and gamma, or our linear stiffness parameters, or our degradation function parameters. And we can assume for each of these, though, a very similar sigma that is uniformly distributed over 0 to 2. Now, if we do this, we can evaluate our parameter uncertainty. And for instance, if we look just at our model parameter beta, one of our shape parameters, we can look at essentially how each one of the data sets, what sort of theta star and sigma star we get from that. So if you remember, this is evaluating that L1 function that's related to our likelihood. This is essentially giving us the mean value or the optimized value based on the data from just that test, as well as uncertainty based on that nice sort of Gaussian approximation. And so here you can see sort of how the values vary and the amount of uncertainty we get with one individual data set. But if we then look at how that affects our hyperparameters, mu and sigma of theta, we can see that we get this nice convergent behavior with the more data sets we incorporate. And we see a similar thing if we look at, say, gamma, right? So we can do this for each one of our parameters. And this is for steel damper pair 1. We can do it for this other steel damper pair as well, right? We can make this evaluation. But what's perhaps more important is if we want to compare the posteriors, once we've included all the data sets, and again, there's 17 data sets total, we can look at the posteriors we generate. And so for steel damper pair 1, we see here for our shape parameters beta and gamma, our posterior distributions, and we can compare this against steel damper pair 2. And interestingly, we see that our means align really well, which is exactly what you'd expect for two supposedly identical devices. However, the building itself was asymmetrically constructed from a superstructure standpoint, so they were not loaded exactly the same. Nonetheless, we get similar mean values, but we do notice there's a different degree of uncertainty associated with each because the standard deviations associated with beta and gamma aren't the same. They're slightly larger with steel damper pair 2 compared to steel damper pair 1. Now, if we look at our stiffness modifying parameters for the X and Y direction, we can see that not only are our mean values highly comparable, but our standard deviations are as well. So our hierarchical calibration here is telling us we have a similar degree of uncertainty as it relates to our linear stiffness parameters or linear stiffness modifying parameters for our two steel damper pairs, which makes sense. It makes sense that these would have a similar degree, seeing as how this is something we feel pretty confident that we know. And then if we look also at our post-yield stiffness ratio alpha or at delta nu, which I highlighted earlier as delta nu being perhaps the degradation parameter that contributes the most, right, has a value that is non-zero. We can compare this steel damper pair 1 to 2 again. And yet again, we see that steel damper pair 2, larger uncertainty, even if the mean values, once we consider all the data sets, are actually quite comparable between these two devices. So we have our posteriors of our hyperparameters. And once we get those, we can actually then just find sort of the marginal distributions of each one of our parameters proper. And if we sample from those, we can then evaluate our degrading Bouk-Wen model. We can then use those responses to eventually get our restoring forces. And if we have those restoring forces, this actually gives us a way to evaluate the uncertainty in our responses, right? We're propagating our uncertainty from our parameters through into our restoring force responses. And this, again, gives us then a way to contextualize this in terms of the actual restoring force itself. So we can compare this hierarchical approach with a conventional Bayesian. And in this case, I'm showing results from test 14, where on the left-hand side here, you see a conventional Bayesian, and on the right hand, you see the hierarchical. And the conventional, this is actually the model selection results we get from our previous model selection study, where we use only data from test 14. We use the full complement of data. And what you're seeing essentially is you can't really see the confidence interval because it basically doesn't exist, because our likelihood function there became so narrow that there's almost no uncertainty associated with the model parameters. And once we propagate that through to the restoring forces, there is essentially no real uncertainty. However, when we use this hierarchical approach, we have a much greater sense of uncertainty if we look at our 99% confidence interval, but this is probably presenting a much more realistic sense of how much uncertainty is present, given the fact that we're incorporating data from multiple different excitations and multiple rounds of testing. Now, the question arises of what if we actually though want to model our error variance directly? So as I mentioned earlier, we had previously marginalized over error variance because we had assumed a non-informative or Jeffreys prior, but we can also assign a probabilistic model to this error variance, right? So what if we said that our error variance was a diagonal matrix where each of the L diagonal elements, and again, we have two elements, one for X, one for Y, was simply expressed as sort of a sigma times A, where A is nothing more than the magnitude, right? Essentially an RMS value of our restoring force in a given direction. And then we use an inverse gamma for our sigma squared, because that's a nice conjugate prior with our Gaussian error assumption. And if we have that, now we have these hyperparameters lambda 1 and lambda 2, right? They parameterize our inverse gamma for our variance sigma squared. And now we can sample from these. So not only do we have hyperparameters for theta, we can have hyperparameters for our error variance as well. And so if we do this, we have a joint prior now where we have to consider our error variance as, again, having its own set of hyperparameters. And that means our joint posterior now becomes a bit more complicated because, again, we have this inverse gamma included as well. And so if we use some methods that Jia et al., Jia and his co-authors put forward, there's actually a way we can marginalize over those theta i's, very similar to what I presented earlier, where we can get an expression for a posterior distribution of our hyperparameters. And I'll admit that it is this somewhat ugly expression you see here, but we can actually evaluate and sample from this distribution using TM-CMC approaches. So now we have a way, because this again is a marginal posterior distribution of our hyperparameters, we can evaluate this using the similar TM-CMC approaches that we used before to get a sense of the uncertainty in our model prediction error variance as well. So what we first wanted though is look at is our parameter distributions themselves. And what I'm showing here is, again, this is one of our shape parameters, beta, and in white you see for steel damper pair 1, in gray I'm showing steel damper pair 2, and then in green, this violin plot is our distribution from using Jeffreys prior. This is actually the same distribution from the previous slides, but now in pink is the distribution according to the inverse gamma. And I found that these violin plots are actually the easiest way to compare multiple distributions on the same plot. But what you can see is that you switching from a non-informative prior to the inverse gamma, adopting this probabilistic model for our error variance, does not have a very significant impact on the parametric uncertainty. Certainly for here, you see our shape parameters, beta and gamma. You can see there's differences going from steel damper pair 1 to steel damper pair 2, just as we observed a few slides ago with that non-informative prior. But going from Jeffreys prior to our inverse gamma, there isn't nearly as much difference. There is some, they're not exactly the same distributions, but they're highly comparable, right? The impact is small or limited, and that is actually what we'd expect, right? And if we look at this as well for our stiffness modifying parameters, we can look at this for our post-yield stiffness ratio, for delta nu, right, which is one of our degradation parameters. I realize the appearance of this violin plot is starting to look a little strange, and so it might be more helpful then to contextualize this in terms of a density plot. But again, we can see comparing steel damper pair 1 to 2, comparing our two different assumptions for how we treat the error variance, we get very comparable distributions, very comparable densities for these model parameters. And so just as before, we can take these distributions, we can find distributions for our model parameters, we can then sample from them, we can evaluate our degrading Buchwin model to find our restoring force estimates. But now we can go one step further, where we can also probabilistically model that error by sampling from our lambda 1 and lambda 2 in our inverse gamma distribution, and we can evaluate that. And what that then allows us to do is to not only evaluate the effect of parametric uncertainty, but also uncertainty as it relates to our error variance as well. So again, if we compare predictions from these different hierarchical approaches, we have our non-informative error variance versus our probabilistic error variance comparison here. And we can see that we don't see a large difference, as you would expect, considering the similarity in their parametric uncertainties. But if we add on the uncertainty when we add the prediction error variance, it is also still quite similar. And this is because we're using observed data, right? There's actually a way for us, even with a non-informative error variance, to evaluate our prediction error. And so we don't really see a huge difference here. And we can do this for other tests that we observed and we see things are comparable. Really where we get the benefit of this probabilistic model of our prediction error variance is for unobserved tests, right? So if we think about, for instance, the Osaka scenario earthquake, one of these tests, this was not included in our data set used during calibration. And now we can not only propagate forward and look at the uncertainty related to our model parameters, we can also do so with our prediction error. And this is something we're not able to do if we use a non-informative prior. So by adopting this prediction error variance in a probabilistic sense, we can now also start to consider unobserved test data and fully consider the uncertainty associated with them from both a parametric and error variance standpoint. And lastly, we can examine the error variance distribution as well, right? We get this nice inverse gamma distribution. And if we identify the most probable value, we can actually compute and evaluate a variance that is proportional or uses this most probable value. And I bring this up because it turns out that if we look at using the MPV there, we can actually see that our original estimate of error variance from our Bayesian model selection, if you recall, I said that was 7 kilonewtons, which as a variance would become 49 kilonewtons squared. This is actually quite an appropriate estimate, as it so happens, because it turns out this is really close to, our uninformed guess is really close to what we evaluate our prediction error variance MPVs to be for all the other test data. So I realize this is a little backwards because now I'm saying that I'm just trying to essentially show that we actually made a pretty good assumption originally in our Bayesian model selection. But I thought this was a nice result and that it sort of, one, validates the robustness with which we tried to approximate that prediction error variance, but two, suggests that perhaps if we had looked at this originally, we might have had a better way to model that from the get-go. However, it looks like we did do a good job taking care of that originally. So in conclusion, we can see that our hierarchical approach allows us to incorporate multiple data sets together, and this presents a more realistic sense of parametric uncertainty. And we can even probabilistically model our prediction error variance, which, while it has a minimal or limited effect on parametric uncertainty, does allow for much more robust predictions of unobserved test data, which can be very powerful, again, if we want to project forward. And then lastly, we just saw this nice result that it returns similar results as our well-founded heuristic guess for the error variance, which I think helps support the model selection results I had shown earlier or previously. So currently we're working towards jointly calibrating over both devices. So we're looking at, okay, what if we take sealed amp prepare 1 and 2? What if we take all that test data and do it together for one joint calibration? And that's something that's ongoing right now. So lastly, I want to talk about multi-fidelity surrogate modeling, again, under uncertainty, because it can often be advantageous to create surrogates where we have a computationally expensive model. Say, for instance, a large finite element model of a four-story base isolated structure. Right, that might be very expensive to have to do a lot of simulation for that, especially if you're trying to do some further design optimization or larger uncertainty quantification. And so scientific machine learning methods like neural networks have become very popular as surrogates, right? They're very expressive, they can work really well. And for instance, things like neural operators are becoming very popular because they are mesh-free and they're built atop neural networks, and that the mesh-free nature allows them to essentially transfer solutions between meshes. And it also doesn't require any knowledge of underlying equations. So if we have just some general governing equation, sort of given an operator notation here, this happens to be a deep operator network. And what a deep operator network is trying to do is to approximate the solution operator for that governing equation. And in this case, a deep operator network, or DeepONet, does that using a trunk network and a branch network working together to come up with a solution operator approximation. And there are cost and benefits to using scientific machine learning surrogates, right? They're very expressive. There's a lot of software tools. Low order optimization schemes like stochastic gradient descent are really wonderful for sort of calibrating these models. However, there are clear challenges related to the amount of training data we actually need, as well as the fact that there are a lot of parameters to tune. However, if we adopt a multi-fidelity mindset, especially for some of these large computational models, we can recognize that we often have ways to express a model in a high fidelity sense, right? Where it's higher computational demand and higher accuracy. And while that higher accuracy helps us generate training data, it's often computationally impractical or inefficient, excuse me, to use that for training the entire network. Similarly, it's often impractical to think that we can generate enough experimental data or have enough throughput to use that to fully train a network or a surrogate of some type. Luckily, however, there are models that exist at lower levels of fidelity. These are often have reduced accuracy because we're using some sort of linearization or reduced discretization, idealization, but they can be much more practical solutions for generating large training data sets. And so the question is, can we leverage the strengths of each one of these model fidelities, right? Can we combine them and harness the efficiency of low fidelity with the accuracy of high fidelity? And so we can consider something like a bi-fidelity deep operator network or DeepONet, where now with our governing equation, what we're really trying to model is our solution becoming the discrepancy between our high fidelity data and our low fidelity model or approximation. And so the idea here is that our DeepONet architecture is going to be used to estimate this correction term, because we're going to assume it's easier to actually learn that than to learn a full high fidelity expression. And note that we can now also do this over uncertainty, because our mesh, whether it's a spatial or temporal variable, can also include uncertainty as one of the variables in our mesh as well. And so scientific machine learning surrogates are well suited for nonlinear systems. Clearly, based on this talk so far, I'm very interested in nonlinear systems. And often one of the challenges we find is that if we have some nonlinear behavior, especially a local nonlinearity inside a much larger computational model, that can really increase the complexity of both the modeling challenge as well as understanding the uncertainty related to that model. And hysteresis in particular forms a very challenging form of nonlinearity because of the memory effects, because you need both instantaneous and your history of past displacements. And so what we wanted to look at was training this bi-fidelity DeepONet for a degrading hysteretic system. I think it's pretty clear why I'm interested at this point in degrading hysteretic systems, especially those under uncertainty. And so what we did is we treated the response from a real degrading system as the true or high fidelity representation of our system, and then decided, well, what if we didn't really understand or know the physics behind that degradation? And therefore we could have a pristine model, which would be our low fidelity model, because it includes no degradation of any kind, but it may be more practical for what we could reasonably assume if, again, the degradation is something we don't really fully understand. And so what the DeepONet is trying to do is learn the discrepancy between our true degrading high fidelity system and our low fidelity pristine approximation. And I'm going to quick go through two numerical examples where we tried to apply this, both being base isolated buildings. Again, can you sense the theme? So we have a 4 degree of freedom base isolated building. You can see here our equations of motion, our model parameters. We're going to excite it using Kanai-Tajimi ground motions, where we're passing white noise through that Kanai-Tajimi filter. And in doing so, we're assuming that there's uncertainty associated with our base isolation layer in terms of our post-yield stiffness, our viscous damping in our base, our ratio of our pre to post-yield stiffness, our yield force. And our validation error metric, we're going to judge the performance of our proposed bi-fidelity deep operator network based on this prediction quantity you see here, which includes both the response from our pristine low fidelity approximation and our approximated or estimated correction term or discrepancy term using our DeepONet. So we're actually comparing our predicted high fidelity response against the true high fidelity data or measurements that we are assumed to have gathered. And we're going to examine different quantities of interest related to this. The first being our hysteretic or auxiliary variable z, because this is right where directly the impact would be felt of this degrading versus pristine approximation for the nonlinearity. And we can see that if we compare the performance of a bi-fidelity DeepONet with a high fidelity one, and in this case our high fidelity is a network trained purely on high fidelity data, where our bi-fidelity is trained on a discrepancy, we see that our bi-fidelity approach outperforms a sort of standard high fidelity only approach by about a factor of 3 when it comes in terms of the mean validation error. Now you might say, well, it's impractical to use this auxiliary variable because you would never be able to measure that in the real world. So touche, okay. Well, what if we then looked at instead the base displacement, right? Maybe a more practical quantity you could actually measure. Well, if you look at the base displacement, again, our bi-fidelity outperforms the standard high fidelity only by a little bit better than a factor of 2. And even if we go up to the roof displacement, assuming we only have a sensor that can measure the displacement of the roof, now we're getting further away from that localized nonlinearity, that localized uncertainty. We still see there's an advantage almost by about a factor of 2 of our bi-fidelity approach over a standard high fidelity only approach. And importantly, we can see and observe that the effect of our bi-fidelity approach is most pronounced the more limited or more unavailable data becomes. Right? The fewer data we have to train on, the more advantageous it is to use this bi-fidelity approach. So certainly if you have a lot of data at your disposal, there's not a huge discrepancy or difference between a full high fidelity or bi-fidelity treatment. But as data becomes more scarce, which is again approaching what the conditions we'd find in the real world, it is more advantageous to adopt this bifidelity approach. The performance gains start to grow. And so we also wanted to look at what happens if we apply this to a larger type model, like a model with more degrees of freedom. In this case, we have 11 stories, 3 degrees of freedom at each story. And so we have 33 nodes in general, which 3 degrees of freedom for each one of these nodes, as well as 1 horizontal degree of freedom at the base. And now we're going to supply excitation in the form of the El Centro earthquake. So we have the same uncertainty related to our base isolation layer, just as we had with our simpler model. But now we're also going to assume that our superstructure is subject to some corrosion degradation. Right? And remember, our original model is going to be completely pristine. It doesn't have any degradation in its hysteretic response, doesn't have any degradation in terms of its superstructure. And we're comparing now, again, our bifidelity only versus a standard depot net. And here we're actually keeping training costs equivalent, because with a larger model, our costs grow. And we recognize that if we have a bifidelity approach, we need 250 simulations, meaning 250 high and 250 low to create 250 bifidelity training data sets. Well, that's actually 500 simulations in total. So we figured it was only fair for the standard DeepNet to be trained with 500, so they have the same training budget in terms of amount of computational time allotted to training. And we find that even if we control for this quantity, the bifidelity approach still outperforms a standard high fidelity only, right? Even if we control for training budget and actually give fewer data sets in total to the bifidelity approach. And the performance gain is maintained even if we add white noise to the signal as well. So what we can see is our proposed bifidelity DeepNet is only asked to learn the discrepancy as opposed to predicting the full response. And this gives it superior performance compared to a standard DeepNet for a variety of quantities of interest, where we're often reducing mean validation errors by a factor of 2 or 3, and our performance advantage is actually even more pronounced the more limited data becomes. And even if we use larger models and control for computational costs, the bifidelity model a bifidelity DeepNet still performs well. And this is even in the presence of noise. And so moving forward, we're looking at, well, what happens if we have multiple levels of model fidelity beyond just 2, as well as starting to use reduced order models to have even lower level fidelity type representations. And so I realize I'm quickly running out of time. So in closing, I just want to emphasize that I think we need to be making our models a little less wrong and a little more useful, whether that's selecting nonlinear representations for isolators, whether it's incorporating data from multiple sets, whether it's figuring out a way to come up with a surrogate representation of a more complex structural model. I think there are many ways we can make our models more informed, more accurate, more predictive, and particularly do this in the presence of uncertainty that goes a long way towards making them more useful. So with that, I'd like to thank my student Reza, my postdoc advisor Eric Johnson, as well as one of his students, Tian Hao, who contributed to some of this work, IG and Tomohiro at eDefense, as well as Professor Day at Northern Arizona, who has been a partner with me on the Bifidelity Depot Network. And so with that, I'd like to thank you all so much for your kind attention and, of course, welcome any questions you might have.
Thank you, Dr. Brewick. It was a wonderful talk. Now it's time for question and answer. So if you have any questions, you can type in the chat box or you can raise your hand, unmute, and ask questions. Yeah, so maybe I can go and ask one question.
Sure.
Yeah, so you choose prior for your Bayesian calibration for the hysteresis models, right? So in this particular topic, I mean, yes, you may have very good priors because this is a very established area. So what happens if you have a new type of damper and existing models may not work very well, or you don't have good priors for this calibration approach?
That's an excellent question, and I regret not spending more time on priors, as I also regret spending too much time on my talk in general. Apologize for the lengthiness. But
No.
so when it comes to that, we actually used uniform priors where for many of them we assumed really expansive ranges in terms of what the values might be, because especially if I go all the way back, the Viana-Rosati model was a model that we were not familiar with at all, and it has a lot of parameters involved. And we had to use really broad priors for that because we didn't have any basis. And Viana and Rosati themselves have only published a handful of papers on it, and they haven't used it at all yet for anything close to the type of application we had. So I think to answer your question, like assuming really uninformed uniform priors, I mean, I realize you can't go from positive to minus infinity, but often we tried to take it within a reasonable range. But this was very much a challenge, and it deserves more discussion. But I'll say that we tried to be as uninformed as possible. But regardless, you bring up an interesting point that, for instance, we struggled with this particular model on what would be a good prior range, and it did require some preliminary analysis, right? Sort of familiarizing yourself with how that model behaves and how model parameters behave. So it's a great question that I did not give enough treatment to. So thank you for the question.
Thank you. I think we have a question from Johanan. Please go ahead.
Yeah, well, thanks for the talk, Patrick. I have a question regarding the multi-fidelity deponent.
Yes.
It sort of reminds me of the Bayesian identification, where essentially you sort of start with a prior model that would be your low fidelity, and you are kind of updating the prediction. But then it comes down to, could you give us an insight about how you would select a low fidelity model? Because usually the high fidelity model is well defined, but then depending on the choice you make for the low fidelity model, it's like exactly the prior model for the Bayesian analysis, right? That might just like a lot. So what's your sense about, like, how do you define a good low fidelity model?
So I think you're asking an incredibly good philosophical question that I'm not sure I can give the perfect answer to, but I will say that often what my collaborator, Professor Day, and I have looked at is how can we come up with a low fidelity model that minimizes the assumptions we have to make, right? Or minimizes the details while still maybe obeying the governing physics that we know to be true. And while I didn't present it today, one example that I have been working on is I have a finite element model of a ship structure where it's used for a finite element code specifically designed for naval architecture. But it turns out that you can also model a ship structure on the open ocean as a floating free beam, right? And so I think about that perhaps better than the case I presented today as a nice example of what a low fidelity model could be. Because in one case, I actually have a very true high fidelity model of a ship based on scantlings and drawings of an actual vessel. But I can also break that down into essentially a floating free beam. And in some work I've done on that, you can actually show that you can get similar modal properties where the mode shape of the beam approximates the mode shape of the ship. The frequencies are similar, but clearly there's going to be a lot of details that you're missing. However, that's an incredibly cheap way or inexpensive way to approximate the behavior of that larger ship model. And in that case, the only real assumptions you're making is that, oh, I believe I understand how these equations of motion should behave. And so I believe I know something about M and K and about how the excitation affects the response, but I don't have any of these details that are going into our much more complex one. So I think from my philosophical standpoint is there a way for us, one way to think about it, I guess then, I shouldn't say the only way. One way to think about it is, are there ways you can represent your system where you're minimizing the assumptions or really relying only on the constitutive relations or the governing equations or the linear operators that you know must apply in this case, as opposed to adding all the other details. So that's one way we've thought about it, at least. I don't know if that fully satisfies your sort of philosophical point, but that's at least one way I've approached it.
Okay. Well, thank you. Great talk. Thank you.
Thank you. Is there any other question? I didn't see in chat. If not, we would like to thank the speaker again. And also thanks to all the audience for attending. Yeah, Patrick, I wrote something on the chat.
Yep, I see it. Thank you so much.
Yeah, thank you. So we'll conclude the webinar here. Thank you, everyone. Bye.
Thank you.